This video is going to show you the solution to an example problem in kinematics where I have two objects running, or basically racing, side by side. Alright, so two runners in a track practice. Randal is running at a constant speed of 9.3 meters per second. Race is ahead of Randal and running at 6.1 meters per second. Randal is approaching Race to pass him. At the instant Randal is next to Race, Race begins to speed up at 0.77 meters per second squared. How much time is needed for Race to catch up to Randal? So let's look at the givens. Look at unit clues and any other clues I have in here. First, I have the word or the phrase constant speed. That means acceleration for Randal is equal to 0. And I have 9.3 meters per second, and going back, that's Randal's velocity. Race is traveling at 6.1 meters per second, and Race is accelerating at 0.77 meters per second squared. So our rule is for every acceleration we have a list of givens. So in this problem, I have two accelerations, one for Randal, one for Race. That means I'm going to have two lists of givens. Now let's look at the question, how much time is needed for Race to catch up to Randal, and that's time. So time is my unknown. So here's a little thing to help you visualize what's going on. They start off side by side, and Randal is moving at a constant velocity. Race was moving slower, now he's speeding up until he catches up to Randal. So at some point he's going to catch up and they're going to travel side by side. That means they're going to travel the same distance across the screen that I have here, and in the same amount of time. And that's going to be important for us. So if I'm looking at my givens, I'll look at Randal's givens. They're the ones in red up here. And if I list my givens, I can see that the constant speed means the acceleration is equal to 0, and the initial velocity is 9.3 meters per second for Randal. So all those numbers relate to Randal, and the time is what I'm looking for. For Race, his numbers are in blue, so I'll make a list of givens for him. Remember, every acceleration gets its own list, and I have two different objects, two different accelerations, so two different lists. And for Race, his is 0.77 meters per second squared, and its velocity is 6.1 meters per second, and time is still the same. It's the unknown. And these two times are the same. 2x is the distance it travels the same, and the times are the same. So here's how you solve it. I take a look at this, and I'm looking for what I have, and I'm going to plug everything into this long equation. And this is the only equation that's going to work for the method I'm going to solve here. And I know to use this equation because I have a little foresight on where I'm going with this. So x equals x naught plus v naught t plus 1 FAT squared. I plug in Randal's numbers from his list above, and I get x is equal to 9.3t. Now for Race, I'm going to do the same thing. Same equation, x equals x naught plus v naught t plus 1 FAT squared. Take the numbers from Race's givens and plug them into the equation, and then he gets a different equation. So do you see how everything's organized as well? It's in two columns, and I've got the givens and the problem, the givens and the problem, so it's easy to follow what's going on. The next step is the trick that I had the foresight to know about. They're traveling the same distance, so distance Randal travels equals the distance Race travels. That means the equation that's equal to Randal's distance is equal to the equation that's equal to Race's distance. So see, it looks like this. The 9.3 goes here, 9.3t, and then Race's equation of 6.1t plus 0.385t squared goes there. Now it's a quadratic equation. To solve this, there are lots of choices. You can use the quadratic formula, some type of computer program, Newton's methods, or you can just use the distributive property. So I'm going to isolate all the like variables on one side, set them equal to 0, use the distributive property to pull out t. So in this case, either t is equal to 0 for the statement to be true, or the stuff in parentheses is equal to 0 for that statement to be true. So if I look at the stuff in parentheses and solve it for t, I get 9.55 seconds. So what this is saying is that when the two x's are equal to each other, either the time equals 0 or the time is equal to 9.55 seconds. And if I look at my picture, that makes perfect sense, because at the time equals 0, at the start of the race, they're side by side. After 9.55 seconds, that's the end of the race, and it's at 9.55 that I'm interested in. So how much time is needed for Race to catch up to Randal? 9.55 seconds. Now your paper is going to look something like this when you write it down. You can see I have two lists of givens, so it's easy to follow. I have givens, math equation, and the numbers in it. Givens, math equation, the numbers in it. And so everything's easy to follow. And then where I combine the two equations, you can see how I made the statement down below. So now I can see exactly what's going on, and you're communicating to me what your steps are in solving this. You got to have all these steps. The list of givens, the equation with just the variables, the numbers, the units, even that x Randal equals x Race, that's got to be there. That's showing me the logic you're using in solving this. And your paper, in total, would look something like this.